Let me remind you one more time, what is a requirement for the aromatic molecule, right? Well, basically the first rule is all the atoms in the ring system must have a p orbital. That means it gotta be sp2 atoms. That could be part of the annular system, double, single, double alternating, or it may have a heteroatoms, and that could be sp2 hybridized. If it's a carbon, then it gotta be charged, okay? Because the carbon is a lone pair, or the, so it gotta be positively charged or negatively charged. So the second requirement is the molecule has to be flat. It needs to be planar structures. And then third requirement is the number of electrons in the pi system is a 4n plus 2. Has to be described by the 4n plus 2. But if that's basically the three requirements, you need to check for deciding whether molecule is going to be aromatic or non-aromatic. So let's use that to figure out if this is aromatic or not. So do you think that it's aromatic or non-aromatic or anti-aromatic? Well, first of all, there's the two double bonds there. So these cover all the four carbons that are sp2 hybridized. Oxygen is there, but you know oxygen can be sp2 hybridized. Carbon here being positively charged, so all the atoms in the ring systems are sp2 can be sp2 hybridized. It could be clear because you just see the 6-member ring. Now the number of electrons, right? 2 from this double bond, 2 from that double bonds. Oxygen can participate and it can offer those one of the lone pairs. The 2 electrons can come from the oxygens. That makes a 6 electrons because of this carbon does not contribute any electrons to the pi system because of the positively charged. So we are talking about a total of 6 electrons in the system, but that has to be aromatic. One of the other simpler way to show it is that you can draw the resonance structures. If you put these lone pairs in here, make a double bond, then this lone pair has to come out and make a double bond. This looks like an aromatic structures, right? So that could be one of the ways also we can use to check if the molecule is going to be aromatic or not. What about this one? And that the aromatic. Well, let me show you the same thing. This oxygen is a lone pair. If you push it in here, you're going to make a double bond between these two. You're going to make this electron pair goes out. So you're going to have a very similar system. So that's going to be aromatic. If you want to count the electrons in the pi system, it's the same thing. These oxygen lone pairs will be used for making pi system. And then the 4 electrons coming from these 2 double bonds, that makes a 6 electrons. So that makes a aromatic system. What about this one? Well, since we're doing the same thing, let's move the electrons and see what happens. We can push the electrons in here and then push that one out. That looks like a benzene type of structures. But if you do that, you have to realize that this oxygen has just a 6 electron in the ground. That is not good for the second row element because the octets are really a critical thing for them. So you don't take electrons away from the oxygen. That is normally a bad thing to do. Right? So this is not good. So that this doesn't happen. So this molecule stays non-aromatic. So it's not just you can move electrons anywhere. It has to have some reason, and then sometimes you can violate some rule, make things a little unstable, like this oxygen having an octet field. All right, there are more examples coming. And let's talk about if this molecule is an aromatic or not. So I hope you can make your mind. And the nitrogen is a lone pair. So what this nitrogen lone pair can do, it can come in and you make a double bond between these two. That electron pairs goes here, and then that pushes electron out to the oxygen. And that's a different from what we have seen in the previous slide, oxygen being positively charged. Oxygen can be negatively charged, still having a full octet field. And then oxygen is one of the electronegative atoms, so oxygen can handle negative charge pretty well. Even that nitrogen is positively charged, but that's different from the oxygen positively charged in the previous slide. These still have 8 electrons of nitrogens. The octets are still filled. So that's not unstable nitrogen. That's kind of okay. Nitrogen can positively charge it if they have a full octet field, then it's okay. And then you can see that now it looks like aromatic structures, and it is aromatic structure. So I hope you can see the differences between the electron movements that doesn't work for the last slide and this one. The second one, you will start seeing something bizarre. Boron. I hope you understand where boron is. Boron is in group 3. You have seen it in the hydroboration in Chem1, but I'm pretty sure you forgot. Boron's group 3. So boron has just 6 electrons in the valence. So borons are naturally electron deficient. Neutral boron only has a 6 electron in the valence, which is a 2 electron short for being octet field. So they always want electrons. And we call that is electrophile, right? That's what the hydroboration happens. We can move the electrons the same way. Nitrogens are basically the lone pairs coming into the system, you make a double bond here. And then these electron pairs goes up, make a double bond with the boron. That makes the boron negatively charged. But that's okay, because the boron, if it's a neutral, only 6 electrons in the valence, which makes boron unstable. But when boron gets the 2 electrons being negatively charged, that makes an octet field. So this is definitely okay. And then again, nitrogen being positively charged, that's fine because these nitrogen still have an octet field. It's not like what we have seen in the 6 electron oxygen being positively charged in the previous slide. So this one is an aromatic molecule to it. What about the last one? I mean, so far, the nitrogens or electrons can come in and they make everything aromatic. So you may think that this one's also aromatic as well. But this is where you have to really check things out. If you do the same movement, electrons of the nitrogens coming into the system, that makes the electron go here, make a double bond with an oxygen. And that makes oxygen negatively charged. But that is, I'm sorry for not showing negative charges here. That's typo. His oxygen should be negatively charged. But that oxygen is really in bad shape. If you count the number of electrons in the oxygen, it's going to be 10 electrons. These oxygens already have 8 there, and you just give a 2 more. So this is a 10 electrons oxygen, which is a violating the octet rule in other way. So you just cannot keep doing the things that you've been doing with the other molecule to this molecule because it's not possible. So that's the reason why this is not happening, and that's why this molecule has to be non-aromatic. So don't get fooled by the similarity in the structures. It really matters where things are that change everything. That's the chemistry. I really hope you see the differences between these examples and understand why this makes aromatic, why that does not. Okay, couple more. Will this be an aromatic molecule? Now we are seeing the 7-member ring, not the 6-member. The 7-member ring system, this is an sp2 hybridized, definitely, because it's a part of the carbonyl. You have every carbon in the 7-member ring is sp2 hybridized. That means, and then it's sort of flat. So we can imagine it needs the first 2 rules of the aromaticity. And then now we need to check the number of the pi system. Having 3 double bonds, it already have a 6 electron from there. So this carbon should not contribute any electrons at all to become aromatic. But the good thing is, oxygen can happily take the electron from the carbon. And that can be seen by making resonance structures, these lone pair making a pi electrons go to oxygens, then you're going to get a charge separation. Is a positively charged carbon with an oxygen negatively charged. And that is the resonance structures we draw, but I think this is probably T-dominant forms rather than the other one. Because this way, you're going to have this ring becomes aromatic. Positively charged carbon does not contribute any electrons to the pi system. So there's only 6 electrons in the pi system that makes this aromatic system. It's a tropylium ion. So even though it doesn't look like aromatic, it is. I mean, so that's the thing. Sometimes, why the alternating double single bond is important is that we want to have all the atoms in the ring system as a p orbital group. In this case, all these 6 carbons definitely p orbitals available. And that is the part of double bond, so they're like a p orbital group too. So we have a 7 carbon, all having p orbitals. So even though it's not alternating double single bond, still it can be a part of the aromatic system. Because in the end, what matters is p orbital availabilities, and then they can be maximally overlapped to make aromatic systems. So this one is aromatic. Then what about that one? It's kind of a very similar looking, except it's a fine ring. So let's see the same way. All the carbons in the 5-member ring can be sp2 hybridized. So, and then it can be flat. So these are first 2 rules. Now, only thing they left to be checked is the number of the pi electron. And then definitely the 2 double bonds. So 4 electrons coming from these 2 double bonds. And then this carbon, we need to decide how many electrons can be given to the carbon. I mean, oxygen has a lone pair, so if you push that where the pi electron comes in, just like in, not going out, comes into the system, then that makes it 6 electrons. But if you do that, then you'll make an oxygen positively charged, which is not good because oxygen positively charged by having 6 electrons is a huge violation of the rule, as we discussed in the first slide of the questions. But if you see it the other way, natural movement of oxygen of the carbonyl is going to the oxygen, so oxygen being negatively charged, is carbon being positively charged. But if this carbon is positively charged carbocation, then only have a 4 electron in the pi system, and that is not mixed aromatic molecule. That actually makes an anti-aromatic. So what that means is this process is not happening because the molecule doesn't want to become an anti-aromatic. They rather want to stay non-aromatic. So this is a non-aromatic.